so we continue with the numericals of force. We had completed till question number 11 last time. So now we continue till for the next one, that is sum number 12. Sum says, when a boy weighing 20 kg sits on one side of a 4-meter seesaw, it gets depressed at this end. How can he be brought to horizontal position by a man weighing 40 gf? So basically it is again a meter rule, but instead of that it is given you that it is a seesaw. So a seesaw will be like this, which will be a 4-meter long. Now of course we know that it will be 2 meters on this side and 2 meters on this side. And they are given us that a boy, he is weighing 20 kgf, is on one side of this particular seesaw. So we need another person over here who is of 40 kgf to balance this particular seesaw. Accordingly, we have the principle of equilibrium as sum of and this is anti-clockwise, so we'll take it sum of anti-clockwise movement is equals to sum of clockwise movement. So we can see over here, this thing is going to be like 20 into 2 is equals to 40 into x, because we don't know this distance over here. This is x, so that is x over here. So this is 40 upon 40 is equals to x. Therefore the man has to be placed at 1 meter from center on other side. Understood? So this is, the seesaw is going to balance only when this man who is 40 kgf is going to sit at 1 meter distance from the center to equilibrium, for the equilibrium or to balance this person who is 20 kgf at 2 meters. Next we see the sum number 13. A physical balance had its arm at 60 length arm and 60 centimeters and 40 centimeters. What weight kept at pan on longer arm will balance an object of weight 100 grams kept on the other plan. So we have over here again, it is a beam balance, but this beam balance is such that it is made in such a way that one side is 60 centimeters and other is 40 centimeters. They are given us that what weight on the longer pen will balance an object at 100 grams on there. So here they are given that this over here is 100 gf. So if I place 100 gf over here, what should I place over here so that it would balance each other? So again the same thing, by principle of equilibrium, that is sum of anti-clockwise movement is equals to sum of clockwise movement. This will be x into 60 is equals to 100 into 40. So x will be equal to 4000 upon 60. So this will give us as 66.666 gf. So a weight of 66.66 gf placed on the other end at 60 centimeters will balance a 100 gf at this particular position. Okay, so this was the 13th sum. Now we see the sum number 14. The diagram shows the uniform meter rule weighing 100 gf pivoted at the center. Two weights are there. So it is given you, the diagram is already given to us. So let's see this one by one. So that is form number 14. They have given a diagram. I'll use the whole board now. Okay. It is balanced. It is given that it is balanced at point O, which is the center. So the center is over here. This is point O, which is the center. And one point is A, 40 centimeters. So from here, 40 centimeters is point A and 20 centimeters is point B over here. Okay, and here the force which is acting over here is, let's say this, take A over here, this is downward force over here and a downward force over here. This downward force is given as 150 GF and this over here is given as 250 GF. So we have to calculate the total anti-clockwise movement, total clockwise movement, the difference in the anti-clockwise and clockwise movement, and finally the distance of O where 100 GS will be placed to balance the meter rule. So there are 4 questions, so we'll go one by one. First one is anti-clockwise movement. This is the anti-clockwise movement. The first thing is anti-clockwise movement is equals to, this will be 150 into 40 is equals to 6000 GF centimeter. Second one, we'll take it as clockwise movement is going to be 250 into 20 is equals to 5000 GF centimeter. Now you can see this being greater, automatically the resultant, that is the question number 3, the difference in the anti-clockwise and clockwise. So we get over here the third point as difference is equals to 6000 minus 5000 is equals to 1000 GF centimeter anti-clockwise. Okay, it is going to be anti-clockwise. Now comes the fourth point. Now they are given us that there is one, now we know that this side is less, this side is more. So this is going to turn anti-clockwise like this. I need to place somewhere over here a 100 GF weight which would balance this thing. So I need to place a 100 GF somewhere here at X centimeters from the center. This is 100 GF. So now I know that sum of anti-clockwise movement is equal to sum of clockwise movement. So this will be, here anti-clockwise we already taken, so we need not write the whole thing again. We can just write over here 6000 is equals to 5000 plus 100 into X, because 100 is this part and X is this part. 5000 we already taken this part. So this anti-clockwise movement and this clockwise movement, and then clockwise has added this thing to equalize for equilibrium. So this will be 6000 minus 5000 is equals to 100x. So 1000 upon 100 is equals to x. So x is equals to 10 centimeter is the answer. So I need to place this somewhere here. So this x will be not here, but it will be here, and so it will be at 100 centimeter from the center. Okay, of course it is on this side. So the answer will be 100 centimeter from the center on right side. Is it clear? So this was sum number 14, quite an important sum. Many sums would be of this kind in boards. So you need to know this thing properly. So this was the anti-clockwise movement, this was the clockwise movement, and addition of this particular weight is seen over here. Okay, is it clear? Okay, now we go to sum number 15. A uniform meter rule of weight 10 GF is pivoted at 0 mark. So this is something unique, and the uniform meter rule is there. This is a uniform meter rule, but this uniform meter rule is such that the pivoted point it as the 0 mark. So this is the pivoted point. This will be 50 and this will be 100. The weight of the ruler is given to you as 10 GF. So that means over here W is equals to 10 GF. So 10 GF is the W over here, which is over here. So this was sum number 15. Now, what movement of force depresses the rule? The force which is depressing it, this is clockwise movement. So moment by weight is equals to 10 into 50 is equals to 500 GF clockwise. That becomes the first part. Second is, how can it be made horizontal? By applying a least force. Now to apply a least force, I will have to apply a force in the upward direction over here. This is xgf which I need to place at this point, so that is the least force. See, if I put it anywhere else, it won't be the least force, because the movement will be maximum only when the perpendicular distance is maximum. Hence, this has to be placed over here. When I place it over here, what will happen? This is the clockwise movement, and this becomes the anti-clockwise movement. So in the anti-clockwise movement, we will be having, so sum of anti-clockwise movement will be having sum of clockwise movement. In the anti-clockwise movement, we'll be having as 100 into x, and over here we'll be having as 10 into 50. So x will be equal to 500 upon 100, x is equal to 5gf. So a weight of 5gf placed on, so weight of 5gf placed at 100 centimeter mark upwards. Okay, you need to write it as upward force, because otherwise this is going to be the same. So it will be, the given will be applying a force of 5 kgf, or we can say not weight, we can say a force of 5 kgf applied, not placed, applied at 100 centimeter mark. Upward force will be required in this particular answer. Is this clear? Right, so it is going to be this way, moment clockwise. Then you need to use the principle of equilibrium, find the answer, and finally you get the final result. Okay, the next one is sum number 16. Now in sum number 16, the most important thing what you can see is that it is given to us that it is a half meter rule. It's a uniform half meter rule, can be balanced at 29 centimeter mark when a mass of 20 gf is hung from its one end. So it is going to you as, it is firstly that it is a half meter rule. So it's a half meter rule over here, wherein this is 0, this is 50, that 25 is over here, and 29 is over here, where there is this particular pivoted point. And you need to find out the mass, that is the W over here, when can be balanced at 20, when a mass of 20 hung it on from its one end. Now we can see, if I place any mass, because of weight over here, this is going to give you an anti-clockwise movement. So I need to place any mass over here, so that the clockwise movement is balancing the anti-clockwise movement. So the first thing is that to identify where will I place this particular 20 gram force. So 20 gram force will be applied on this side, because already the weight is acting on this side. So the 20 gram will be somewhere over here, that is 20 grams. That is not somewhere here, it will be exactly at the 50 mark. So at 50 mark there will be this 20 grams. So first of all, they are given as a diagram. So ask the diagram. So this is the first answer itself, the diagram itself. And the second one is to find the mass of the man. So again the same thing, sum of anti-clockwise movement is equals to sum of clockwise movement. This will be giving you as W into 29 minus 25. This is the distance, not 25, right? Is equals to 20 into 50 minus 29, because this distance over here. So this one over here is 4W is equals to 20 into 21. So W is equals to 20 into 21 upon 4, that's 5. So W is equals to 105 grams. So the weight of the ruler is 105 grams. Is it clear? So that is the weight of the ruler, 105 grams by this method. The next one is sum number 17. Okay. In sum number 17, we can see over here that a uniform meter rule of mass 100 grams is balanced on a fulcrum at mark 40 centimeters by suspending an unknown mass m at 20 centimeters. So it is given to here us that this particular uniform meter rule is such that this is 0, this is 50, this is 100, and it is balanced. The mass of the ruler is given as 100 grams, so at 50 you have got this mass which is 100 grams, and it is pivoted at 40 centimeter mark. The fulcrum is at 40 centimeter mark. So this is the fulcrum over here at 40. And you need to place something over here. Now of course this is going to be fulcrum यहाँ पे equal to है, इसलिए all these forces are acting over here clockwise. So you need a anti-clockwise movement. Hence you are placing a 20 centimeter mark a mass of m. So this is m which is placed over here. You need to find out first the value of m is what you need to find out. So first the value of m. So first is that sum of anti-clockwise moment is equals to sum of clockwise moment. So this becomes m into 40 minus 20 is equals to 100 into 50 minus 40. That's the distance, this much. This is this much. So here it is 20 m is equals to 100 into 10. So m is equals to 1000 upon 20. That gives me 50. So m is equals to 50 g force. So this is 50 grams of force will be there in this particular case. So m is 50 grams. The next is to which side of the ruler will tilt if the mass is moved to mark 10 centimeter. Now if I move it to 10 centimeter, now if I move it to over here, then what will happen? So you can see over here that if I move it this way, here at this particular point it is at equilibrium. Now the moment this thing becomes 30, then what will happen? Automatically the anti-clockwise movement will increase. So by moving it, so if m moved to 10 centimeter mark, the anti-clockwise movement will increase, and hence tilt anti-clockwise. Is it clear? So the answer would be that if I move it on this side, then on the side of to which side of the ruler tilt with the mass m is moved? Yeah, so that will be on the side of the m side. If I move it to the m side, then it will be so it will be anti-clockwise, or we can say just say it is towards the m which is going to tilt downwards. The next is what is the resultant movement now? So the resultant movement over here, so we will say over here again, the resultant movement will be, so now anti-clockwise is equals to now initially it was, so this is nothing but 50 into now 40 minus 10, so is equals to 50 into 30 is equals to 1500 gram centimeter, whereas clockwise we already measured it as 100 into 10 is equals to 1000 gram centimeter. Therefore result is equals to 1500 minus 1000 is equals to 500 gram centimeter anti-clockwise. Okay, that's the result, that it will be 500 gram force anti-clockwise movement. Finally, how can it be balanced by another mass of 50 grams? So now I need to put something on this side. I need to put something on this side, only then it will be proper. So if I place something over here, then what will happen? It will be this way, that 1500 is equals to 1000 into x. Okay, I'll say the mass first. So if I take this as point x, and you are going to put a mass of 50 here. So this is 50 grams. So it will be 50 into x minus 40. So this will be 500 because 1000 comes over here. So make it 500 is equals to 50x minus 2000. So that will be 2500 upon 50 is equals to x, so x will be equal to 50 centimeter mark. So when I place another mass of 50 grams at 50 mark, at that time the whole thing will be balanced again. Is it clear? So this was again a very important sum. Okay, now we come to the last question. The last question is quite easy because here you do not have movement as such. The main thing, in fact, the answer is already given in the textbook. The textbook has already given you as a hint the answers. So it is this way that you have got, Radian's question is, you have got a meter rule over here, and the meter rule is such that this weight of the meter is acting over here, W over here, and you have got two fulcrum now, one fulcrum over here and one fulcrum over here. This fulcrum will be such that there will be a resistive force over here, R1, and a resistive force R2 over here. So we know very well that when these two things are there, this W is going to give one force on this side and one force on this side, so that both are going to be in equilibrium. Accordingly, what we see over here, that in equilibrium, when it is in equilibrium, what will happen is that the force R1 plus force R2 will be equal to W, because the W is getting distributed equally on R1 and R2 because the mass is getting settled over there, and because over here the W is at the center, so if this is the length L over here, then this distance over here will be L upon 2 and this will be L upon 2. So what will happen will be that R1 force into L upon 2 will be equal to R2 force into L upon 2. Right? So what will happen is that we get this cancelled. So R1 is equals to R2. If R1 plus R2 is equals to W and R1 is equal to R2, what will happen? 2R1 is equals to W, or R1 is equals to W upon 2. Therefore, R1 is equals to R2 is equals to W upon 2 is the answer. So W upon 2 is kgf is the answer. So what is the question was that? Then in equilibrium, find the reaction R1 and R2 at the ends. So R1 and R2 at the ends would be W upon 2 kgf on this side and W upon 2 kgf on this side. Okay, that's the end of this particular part of the chapter. Okay.